this wonderful conference. I really enjoyed it. And it maybe should be an opportunity to start more collaborations in the heart of Europe. Vienna is not very far, for example. Trieste is not very far. So, but cool. So today I will talk a little bit about stuff that we in Vienna are very excited about at the moment. It's really just an excuse for me not to work on hydro simulations, so I can keep doing in-body simulations. And but it's really cool to see that effectively we can fit in-body simulations to observation or so to survey data. And I guess the date 2009 is wrong. It's just a typo. You get a message from the past. It's the same talk for the last 15 years. Yeah, so this work done in collaboration with Florian List, who is a postdoc for the last 2 years in Vienna, who has done most of the heavy coding, Thomas Flöß, who joined us last year, Cornelius, who now moved recently to Croatia, to Zagreb, and then PhD students Lukas Winkler and Alejandro Estela Yesta, and also involved was Natalia Porkelis. So we're interested in the modeling side of everything. And so if you think about what we observe in the end, how do we get there, and what do we have to model? We have sort of the early universe physics, which we call CMB, which is linear. So physics, we can treat it completely perturbatively. Then under self-gravity, so we have the motion of fluid elements, formation of galaxies as the tracers, which gives the cosmic web and all the large-scale structure. Which, well, you go from linear, you go to mildly nonlinear, and then if you go to very small scales, then it becomes very nonlinear. So much so that perturbative approaches break down, and you have to think of something better than this. So, for example, simulations. And if we want to make the full connection to the galaxies so far, the best thing on the modeling side we have is simulations. But I don't think the picture is fully self-consistent. And so what we want to have in the end is we want to describe all of this, we observe this, and what we want to get out is the parameters of the model, right? As the optimal compression of the universe into some theory assumptions and some parameters. Ideally, 0 parameters, but that's more a philosophical question. Exactly. And so we want to have the mapping between basically the physical model and the observables, and constrain all the parameters as good as possible. Ideally also taking into account all uncertainties in the modeling side and all cross correlation. So I don't think we're there yet. Some of them might actually not be important, but in the end, you want to know whether galaxy formation efficiency also depends on some details of multiple parameters. Exactly. And so in some sense, the limitation right now, I think, comes mostly from the modeling in order to get the maximum information already with existing surveys. And of course, we have a lot of observables, and also that's not fully leveraged, that they're all kind of coming together and are analyzed in the same framework. So that's also something that will have to be done at some point. Exactly. So we had already a talk about compression of data, and this is just for maybe the younger ones, maybe otherwise obvious statements. So for the CMB map, you don't need to store this data, the map data here, because there's effectively not much information here because it's purely Gaussian, so you can compress it fully and then you can isotropically average it by saying there should be no preferred direction, and now you get your power spectrum, and so all the cosmological information that can be there is here, and all the anisotropy is within into the error bars effect. Sorry, the rotational degrees of freedom. So if the ICs are Gaussian and structure information is linear, that's all of the information. This was the beginning of precision cosmology. I think with this now you get sub% constraints on cosmological parameters. If you look at the late universe, it's very different. So it looks like this. Maybe you can take the log, but even if you take the log, the 3-point function doesn't really vanish. It just sort of becomes less important and so on. So how do you now compress the data here? And so people thought about many ways, and we've heard about some, right? So you can add, for example, indicator functions, but also skew spectrum. Nobody talked about skew spectrum. Wavelet scattering transform is another one, whether sort of they are unifiable. We had a discussion yesterday, KNN functions, but also more sort of, I would say, astrophysically inspired ways of looking at things. Maybe the most traditional one, cluster mass functions. I don't think, is anyone here working on clusters? or it's not so fashionable maybe anymore. But voids are very fashionable, and I learned exactly. And then also sort of the more agnostic of all of these is the standard sort of moment expansion in spatial statistics. So these ones you can model very well with perturbation theory. Many of these here are difficult to model actually with perturbation theory, especially once you also take very nonlinear information. So yeah, so that's a choice. Including information beyond the power spectrum, however, is sort of critical to. So this is just an example. I should take maybe from Ishmael's paper. But the wavelet scattering transform, this is just the usual corner plot, doesn't really matter what's here. But this is the expected improvement on parameters going from power spectrum analysis alone to a wavelet scattering transform. So you get much more information in theory. The other idea is to not compress at all, but do the full field level inference. And of course, I'm not the first one to do this. There's some tradition in this. The idea is you write the whole thing down as a basic inference. So of course, theory probability not only for your cosmological parameters given your observational data, but also you have to infer, because now you're working at field level, so you're not marginalizing over field realization. So there's no predicting some statistic anymore. We split this into likelihood and prior. And so this allows you now to reverse this. So given a modeling of the sort of a choice of initial conditions and a choice of cosmological parameters, you have to predict the data. And you can do this then with a Bayesian inference framework. Problem is this one is below dimensional. This is relatively high dimensional, but there is techniques to efficiently treat very high dimensional spaces, so multi-million or even billion dimensional spaces. Principle. So the reconstruction aspect, so without the theta, this has actually a fairly long history going back. I think the first ones, at least I'm aware of, to do this with a Bayesian framework is Paco Kitaura, Thorsten Enslin in 2008, then which was picked up by some board collaborators. Exactly. So far, nobody, I think, has managed to also constrain cosmology yet. Okay, well, we'll see whether it's doable. Okay, so in the end, we want to now solve the cosmic inverse problem that I formulated. So we start with model parameters, noise realization, we evolve it forward, predict our observables, predict all ground effects, selections, and so on, and then to go back using Bayesian inference. Why do I think this is preferable to a sort of classical reconstruction technique? Because you're sort of, in the end, what you observe is very incomplete. And so you don't have to worry about the inversion being unstable to completeness and uncertainty. In the forward way, you just have to look for sort of consistency. Exactly. So two approaches typically are employed to invert this. One we've just heard this morning in other talks, simulation-based inference. So the idea is you run this forward and you learn the mapping between the two. The cool thing is here you don't have to do the field realization. So you can go directly into the cosmological parameters. That's what Zoltan was mentioning. Effectively, we often call simulation-based inference or implicit likelihood. So you have a neural network that even in global explicitly returns the parameters. Or the other one, that's the classical Bayesian inference more, is that you write down your posterior likelihood, take the log of it, and then you Monte Carlo sample it using efficient techniques like Monte Carlo. For each of these, whatever you choose, you need a very fast forward model. So if you choose the second one, your forward model also has to be differentiable. If you choose the first one, it doesn't have to be differentiable. Still, it should be fast. Why? Because we have to show probably 10,000, 100,000 realizations, depending on the high dimensional parameter spaces to a neural network. Exactly. Good. So this is sort of what we worked on for the last year. We're not the only ones again. This is sort of the core team. So Disco DJ, the framework, parts of what this line Disco, differentiable simulations for cosmology, done with JAX, and also because everything software that we publish is music related somehow. So one part of it, we'll talk briefly, it's already public, so you can just download and use it. It's a fully differentiable Einstein-Boltzmann solver. It's slower than Class or CAM at the moment because it's not so much optimized. But it's much easier to add your equations to yourself. So if you want to extend new physics and so on, it's super trivial. And then there's a nonlinear model, mostly written by Florian, an LPT to arbitrary order and full n-body solver, and probably also multi-GPU at the moment. And there's of course others, like for example the DAX PM, sort of this part of this sort of does this part here as well. So there's several things on the market. Exactly. So I showed already at the beginning that we coupled sort of different physics together, and because we can't do this yet in one framework, so that's why. So there is still this module where we solve the early universe physics, and then you learn solve the early, not talking about inflation. And so in one module you have all the GR effects, so relativistic species, horizon scale effects, and so on. Photon-baryon coupling, recombination, everything has to be modeled. And you have a very different flavor, but everything's linear. And you have a very different flavor where basically it's just perfectly cold fluids, but very non-linear. So different flavors of perturbation here have to be employed. And then you have to piece this together. There are several ways. I can talk about this, but it will be very technical. Let's just skip over this and just show you cool things you can do if you have a differentiable Einstein-Boltzmann solver. Because you can, so here is the scale, and this is time, a scale factor. So Big Bang is up here, today is down here. And so you can just see what's the response as a function of scale and time of the matter power spectrum to changes in the cosmological parameters. So for example, if you change the helium abundance, then you see there's sort of a change in the amplitude of the BAO a little bit. If you take parameters, you can't see anything. These are like a dark energy equation of state parameters. They don't change anything early on, but they change things in late times and so on. So you figure it in the paper. So this actually implements the equations. There's other ways you can achieve this with other Cosmo power jacks, just as an emulator. So if you have say Gaussian process regression, you can take gradients of that trivially. So if you have an emulator that fits the power spectrum, then you can also take gradients of that, of course. Once you have that, for example, maybe your Fisher forecast is trivial, no? Because you can just sandwich your two gradients with a covariance matrix, precision matrix. Fisher 3 minutes to run to reproduce the Euclid spectroscopic predictions. We have one parameter which doesn't match. I can find the bug. But this was very nice to see. And you don't have to do weird things with finite differences and yada and so on. Exactly. One thing was the first version actually didn't match. And then I had to talk to Julien Lesbourg, and they included neutrinos, and so they updated and so on. And found that actually we only agreed with their prediction, not with the original forecast. Okay, so now we have to come to time. Nonlinear evolution of matter. So this now we can predict power spectra at any given time, take gradients. So there we have two choices. One is fluid model, where basically say, well, I have a continuous patch of early universe matter, and then it evolves into a continuous patch of late universe matter in some way. And so you model this mapping between them. Or you do an n-body approximation, which says, well, I'm solving this not for the continuum, but I'm solving it for a discrete set of what mathematically would call characteristic curves, along which the space-based time is conserved. Exactly in the end, then say, well, this connection hardly approximates this mapping. If you want to read more about this, all the details are in this review article that we wrote, Roland Bloom and I wrote some years ago now. Exactly. So typically, this is done in Lagrangian perturbation theory, that you actually try to calculate this mapping perturbatively. So you write down some fluid element starting here, moves to here, and then how does the density change? Well, it's just given by the Jacobian of the transformation. And then this going from here to here, you expand this in some kind of Taylor series, where now you have time-dependent pieces and you have spatially dependent pieces. So these are basically spatially dependent Taylor coefficients, if you want to think about it like this. So these have been originally derived 2 LPT, 3 LPT, and so on. But now we know there's actually recursion relations, and once you know at one order, you can calculate the next order. And then if you picture them, the spatial coefficients actually looks like this. So for me, from the data science brain, this looks quite wasteful, because you see, well, sort of there is a big difference in the spatial structure, but then not so much anymore once you go to the higher order ones. And so why is that? actually these points that survive are regions where you have very slow convergence, and this is close to peaks where you have close to spherical collapse. So the centers of voids, where the clusters form, and so on. Exactly. And so one question, very academic maybe, that we ask ourselves, why is that? So you can do, you all calculated this if you took a cosmology class, the black curve, that's your spherical collapse model. And you all know this parametric solution to it, right? I guess, which is just the cycloid curve. The funny thing is there's symmetry. If you go backward in time, so negative A, then you get the hyperbolic solution for the endodens region. And now you see what's actually happening is when you solve the same equations with LPT, you get sort of these curves. Here they approximate like this. So here you see there's a singularity here. So you squeeze in. Now remember your first year mathematics about convergence of spheres is always limited by the disk in the complex plane, not by this point. So of course it also diverges for the voids, even though there's nothing spectacular happening. It's just because of the symmetry of the equation. So now we understand that. So this breaks down, and you have to watch out about convergence when you're close to peaks. Never mind the details. Okay, so this is nice, but we cannot go arbitrary and nonlinear with this, right? So we can predict large scales, but we have to watch out. But we are still in the convergent regimes, which means we have to either cut in space or cut in time. If you want to go further, you have to use something that's like an n-body simulation. But there the idea is that you, instead of expanding around a equals 0, so your initial power, you re-expand at every time step. Because you use the computed density field to re-expand your equations. And so instead of sort of having a trajectory that's smooth, you move assuming the matter doesn't move. Then you compute how your matter would sort of, one interaction would change. You kick your particles and then you move them again. And then you have some freedom, so you write out these equations. So now there's something interesting that we noticed, is that if you were to do this in perturbation theory, you do a certain way. If people run n-body simulations, they do it in a very different way to sort of approximate these trajectories. And this causes it to be inconsistent. So if you remember, Zeldovich approximation moves particles on straight lines. An n-body simulation would also move it in a straight line, but in a way that you always kind of overshoot in velocity and then undershoot again. So you need to converge basically to a straight line, which is very stupid because you should just be on the straight line. And so you can build perturbation theory by sort of modifying this. You can build it into the integrator, and that gives you huge advantages. Let me show you this. So if you predict, say, large-scale structure in a very nonlinear regime with 2 LPT, it looks like this. So all the Shadrow stuff looks terrible, right? All the structure is diffused out because it's wrong. So the only way you can save this is by saying, I cut out the small scales and I'm only looking at the large scale evolution. Then with this new time integration scheme, if you do one time step, you recover exactly the same result. Now, if you do more, you converge towards the true thing with very few steps. While in a standard n-body simulation, if you were to also do very few steps, you see, you get small scale structure, but the large scale structure is completely wrong. So we know this large filament structure is completely missing. And why is that? Because you're actually not consistent with the perturbation theory. So what's the difference? So this is a power spectrum. Now let's just look at this. Too many things. So if you run your gaseous simulations, your power spectrum converges independent of K from the bottom. So if you don't do enough time steps, even on the largest scales, you're wrong. Now, if you build the perturbation theory into these integrators, you converge that on large scales is always asymptotically correct, and the more time steps you do, the more accurate you get on small scales, and you can actually prove this behavior. And then you can do choices. You can say, I want to be consistent with first order perturbation theory, but I want to also be symplectic. Or you can say, I don't care about symplectic. I can be consistent, use that additional degree of freedom to be consistent with second one. Yeah, so this is now nice because you can do, say, I want to be accurate at, so here we have, this is 0.02% or something like this, 2 per mil. So if you want to be accurate on the scale, you have to do 10 steps, something like that. So very nice. But there's another problem. You have discrete particles. Well, actually, let me skip this. I think we don't have enough time. So ask me about this later on. Exactly. So the other cool thing is with this, actually, your simulation, because you're doing things differently, stays regular in the A to 0 limit. So you can actually start your simulations in principle from the Big Bang. So just for fun, we computed the forward light cone of a particle because everybody just shows the light cone of an observer, right? Where around you it's redshift 0. And then as you go out, you go to the high redshift. So this is the particle basically on the particle horizon. So the particle light cone. So for a photon starting at the CMB or shallow photons, what would they observe? So and you can only do this because you start where it's more of a just showing off, really. Okay, next problem is, of course, now we can model matter arbitrarily accurate by adding more and more time steps, but we don't have galaxies. So what can we do with galaxies? Well, we could I do my examination, but I don't think we want to do that because that's why I started this business. Semi-analytic models, you need merger trees, you need halos, too complicated. You could do some density. So this is actually from a review of Wexler and Tinker. Abundance matching, halo occupation. You could do all of this, but the main problem is you need halos. And in order to get halos, you have to resolve dynamical time scales, which are actually not interesting for large-scale structural cosmology necessarily. So something that's sort of more interesting is, can we do something more abstract? And so hydro simulation is too expensive, too many parameters, but even sort of halo models and so on, too expensive. Can we do something more abstract? And so the one very elegant way is this effective theory of galaxy formation, where you say, I want to describe my galaxy field in terms of all possible operators that can act on it. And I expand it perturbatively. So I say, well, at first order, the density of galaxies in a fluid element is proportional to the density of matter. Then you could be responding to whether this is locally a fluctuation, variance, local tidal field, local curvature of your density field, and so on. So these are spatial operators, and these are coefficients. And now you just put this together as a linear combination, and you say, I fit these along with my cosmological amplitude. And so now you can basically put all of this together. So you just draw your initial conditions, you forward model it with a linear, you apply some scale cuts, then you compute your spatial operators, you advect this with the n-body, you get your final probability density of the galaxies out, and you combine this together with your data into a likelihood, and you sample this. And so, well, when you do this is just a toy example not published yet, so it's a work in progress. You generate mock data from the Halo catalog, and so what we found with this now, we can sort of see that even with very conservative scale cuts of 0.1, you can do in the order of this is a power spectrum plus bispectrum Fisher analysis. This is just sigma 8 matter of B1, so quite competitive. And on top of it, you get all the initial conditions, of course, that are consistent with your observed galaxy sample. So, for example, Fabian-Schmidt's group, they're doing very similar things, but using Lagrangian perturbation theory instead of n-body simulations as the forward model. This is just, everything's too small here on the screen. If you want to constrain FNL, you can even show this paper. Thomas Fliss is preparing it now. You can even show that your constraints on FNL will improve quite dramatically. And that's very interesting because FNL typically you get from large scale constraints. And so if you can get out more information than power spectrum plus bispectrum from small scales, that's much cheaper than running a larger survey in order to get more nodes. Exactly. And so in the end, we've been playing a little bit. This is now BOSS low Z plus CMAS. You can just do a reconstruction. And so the nice thing is, thanks to JAX and everything running super fast on a single GPU at the moment, so we can draw 10,000 samples in under a day in order to sort of do games like this. I think we're running out of time. So put out the summary and conclusions. So just to remind you, we're putting this framework together. Oh, this could each forget. Einstein-Boltzmann solver exists already. Feel free to download it, play with it, add things. Write to us if something doesn't work. Write to us if you improved it. There is the nonlinear model. Florian has the paper almost ready, and once the paper is accepted, everything will become public as well, which includes the full and-all IPT recursion and these new time integrators and PM simulation. So you can do a 512 cube particle one time step in 0.2 seconds, A100 GPU, which is, I think is quite comparable to JetPM, also NNG. Exactly. So when you put them together now, you have the full, basically simulation from Einstein-Boltzmann to late times. Exactly. Open problems, if anyone's interested. One thing would be great if we could sort of improve the conversions on small scales. Right now, the only way to do that is many, many time steps. Minutes, so much. Including the discussion, I speed up. Okay, so it's very small nonlinear scales. So, for example, using super resolution machine learning techniques could be something like this, because all halo, there's no hairs here on the halos, and it's like only concentration and mass. Or other sort of small scale models that we could put in. Baryons we've heard, and also unsolved. Could put also machine learn or parametric verification models on top of this. Part of it is already captured by this effective expansion in the bias parameters. Another thing that we were wondering about is not really solved yet is if you want to predict mass functions. Mass function is something that's not trivial to calculate in a differentiable way. So another trick there is that you can label fluid elements, what mass they should belong to, and by doing that you can provide a master student. I recommend you to check that out if you're interested. Good, thank you very much.
Have you tested really that for highly nonlinear space, you really can reach to 1% accuracy for increasing number of time steps?
Yes, we can.
So, like,
it just needs many.
How high was the K?
So the largest is K of 10 or so that we checked. Yeah. But then you need hundreds. Yeah.
Maybe related, but can you give an idea of the CPU time required to go to this higher order?
That's LPT is fast. I don't know the numbers, but it's also on the order of sub-seconds and so it depends on the order as well that you go. It explodes very quickly, right? Because your things goes quadratic with the order. So the number of fields that you have to compute. And in practice, beyond 3 LPTs, that actually relevant, except when you want to do convergence tests.
Any other questions? Okay, so let's thank the speaker again.